So as mentioned, we will talk about some equivalencies regarding eigenvalues and eigenvectors and other theorems that that you look at in linear algebra. So we already know that AV is equal to lambda V for all eigenvalues and eigenvectors. And we can, this is true if and only if AV is minus lambda V, oops, not this very ugly lambda, very V, V is equal to 0, and that's 0 the vector, not 0 the scalar. Now, before we continue this, we have to have our assumption from previously, where V is not the 0 vector, and lambda is in the real numbers. And again, this implies that AV minus lambda IV equals 0 the vector. And I just stuck in a identity matrix here, and that is true for any n by n identity matrix, because multiplying anything by the identity preserves the original thing you're multiplying. And now I can, by distributive property of matrices, I can take out the v. So we have A minus lambda I, v is equal to 0 the vector. Now, this is a very special matrix that I've been talking about earlier, A minus lambda I. It can also be expressed in the other direction, but we're going to worry about this for now. Now, since this is equal to 0, this means that V is in the null space of V is in the null space of A minus lambda I. Now, and we also assume that V is not the 0 vector, therefore, the null space cannot be equal to just the 0 vector, because V is not the 0 vector. So therefore, there's something as a dimension of at least 1. And since it has a dimension of at least 1, then we know that the determinant of A minus lambda I is equal to 0. And for the astute, you'll also notice that since this is true, A minus lambda I is not an invertible matrix. So let's look at this equation. It's a very interesting equation, and it will actually help us find the eigenvalues for any A, if they exist. So once again, determinant of A minus lambda I equals 0. Now this is what we refer to as the characteristic equation, where the values of lambda that satisfy this are the roots of the equation. And this is known as the determinant, the characteristic polynomial. So let's look at the values from our previous example. I'm going to write them over here. A is equal to 1, 1, negative 2, and 4. And we know that the identity matrix is just 1, 0, 0, 1. So let's look at, and we know that our lambdas are 2 and 3. So let's look at this equation with lambda equals 2. So A minus 2I is equal to, what is it, 1, 1, negative 2, 4, minus 2, 0, 0, 2. And we know that is negative 1, 1 minus 0 is 1, negative 2 minus 0 is negative 2, and 4 minus 2 is 2. Right? Yes. No, I did that completely incorrectly. Come on. Let's backtrack. So we have A minus lambda I is equal to, this just scales I, so that becomes 1 minus lambda, because lambda times 1 is lambda, and becomes 1 because 1 minus 0 is 1. This stays negative 2, and this becomes a 4 minus lambda. Right, so that is, I'm multiplying A by lambda I. And I claim that the values of this equation for lambda that satisfy this equation are 2 and 3. So let's look at the determinant of A minus lambda I. And since this is a 2 by 2 matrix, I could take this diagonal and subtract these two numbers multiplied together. So we have 1 minus lambda, 4 minus lambda, minus a negative 2, which equals 4 minus lambda minus 4 lambda plus lambda squared plus 2. And if you simplify that down, that goes down to lambda squared minus 5 lambda plus 6. Now, if you notice, this is factorable. You get lambda minus 2 times lambda minus 3. And the roots of this equation are 2 and 3. Therefore, our eigenvalues for the determinant of A are 2 and 3. Now, why is this useful? Well, we can use these eigenvalues to compute the basis, to compute the null space of A minus lambda I. And you will notice that the null space of A minus lambda I are actually the eigenvectors. So let's show that. So let's let lambda equal 2. I'm really bad at drawing lambdas, I apologize. So 1, 1, negative 2, 4, minus 2, 0, 0, 2. And we have 1 minus 2 is negative 1, 1 minus 0 is 0, negative 2 minus 0 is negative 2. This should say 1. And 4 minus 2 is 2. Right? So now we can set this matrix that we just put in, I'll write it here, negative 1, 1, negative 2, 2. And to compute the null space, this is the equation for computing a null space of any particular matrix. So we know Gaussian elimination. We can do this and augment the matrix, and we can quickly see that 1 is a multiple of the other. So I can take negative 2r1 plus r2 and put that into r2, and we get the following. So the top row stays the same, and this just becomes a row of zeros. And from this, I can see that negative x1 plus x2 equals 0, or in other words, x1 equals x2. So we know that with this, our v in this equation is equal to x2, x2, since x1 is equal to x2. And now we can factor out an x2, and we get 1, 1, which is one of the eigenvectors we saw in the previous video. Now, let's, that could just be a fluke. Let's do it with the other one with a lambda equals 3. Lambda equals 3. So now we have, again, 1, 1, and negative 2, and 4, minus 3, 0, 0, 3. And again, 1 minus 3 is negative 2, 1 minus 0 is 1, negative 2 minus 0 is negative 2, and 4 minus 3 is 1. And again, the same thing will apply. x1, x2 is equal to 0, 0. And again, once again, we know Gaussian elimination, so we can do this. And I could just take negative r1 plus r2 goes to row 2, and that yields negative 2, 1, 0, 0, 0, 0, just like in the previous example. So now, if we take this information, we know that negative 2x1 plus x2 is equal to 0, or 2x1 is equal to x2, or x1 is equal to 1/2 x2. So now, we can say that v is equal to x1, x2, but we know that x1 is equal to 1/2 x2, so 1/2 x2, and then x2 is just x2. And now, I don't really like fractions, and I'm sure neither of you do as well, so we can just multiply both entries by 2 to get x2 and then 2x2. Right, let me look at my situation here. Correct. And now if I just take the x2 out, and you get 1, 2, which was our other eigenvector. So by finding the eigenvalues with the determinant, we can find the eigenvectors by computing the null space of these matrices with the corresponding eigenvalues you get from the characteristic equation. So now you may say, well, why is that important? Why is that useful? Why go through all this computation? Well, now we have a basis of eigenvectors. Instead of using the standard basis for everything or trying to do some weird base changes, we have a basis of the eigenvectors. So we have it for reference, I'm going to set our eigenvector set to be 1, 1 and 1, 2 from the example we've been working with so far. So now let's let x be any vector in R2, right? So we have any vector in two-dimensional space. So we have x1, and let's let x be expressed as a linear combination of our eigenvectors. And we can do that because it is we're using this as a basis, and this is in R2. And now if we multiply both sides of our matrix A that we had previously, AC1, 1, 1, plus AC2, 1, 2, right? And now we can reassociate. We can reassociate our vectors by associative properties. By the way, we know what these are. These A11 is just 2, 1, 1, also known as 2, 2. So we know that this is C1, 2, 2, plus C2, but we know that A12 is equal to 3, 1, 2, which is equal to 3, 6. So now we know that AX is equal to C1, 2, 2, plus C2, 3, 6. Now any vector multiplied by the matrix A can be expressed as a linear sum of our eigenvectors. And we know that because any other parallel vector is also an eigenvector.